In the last episode, you told me how motion slows down time. I understand that. But gravity? How does gravity affect time?
Before asking why gravity slows time, you must know what gravity is.
Well, I know what it is. It's a force that causes objects to fall.
And that's exactly where you are wrong. Gravity is not a force. And it's not a force that causes objects to fall down.
Well, if gravity as a force doesn't exist, and it's not a force that causes objects to fall down, then what is it?
To understand that, and what exactly gravity is, there are a couple of things that you should know first.
Like what?
Like understanding that everything that exists is always in motion, even if they are still.
Wait, if they are still, how are they in motion?
Still in space, but moving through time.
How is moving through time considered motion?
In the universe that you think exists, it is not. But that universe doesn't exist.
I don't get it.
See, Zane, in our universe, space and time aren't two separate things. They are woven together to form the four-dimensional framework of our universe called Spacetime.
Oh, space-time. I've heard the term a lot. The fabric of space and time.
I am sure you have. But it's important to remember that space-time isn't actually a fabric. It isn't a material you could touch or see. The fabric is just a visualization aid.
Then what is it?
That's the difficult part. There isn't a picture you can hold in your mind that's completely accurate. Space-time is four-dimensional, and our brains evolved to visualize only three-dimensional space. We can understand it mathematically and describe how it behaves, but we can't truly picture it.
Okay, that's fascinating. Is there anything else I should know before we get to gravity?
Yes, one last thing.
And what would that be?
When an object is moving through space-time and is left undisturbed, it always follows the straightest possible path available. We call that path a geodesic.
So, the straightest path between 2 points in space-time is called a geodesic?
Exactly.
So, if I've understood correctly, everything in the universe is always in motion. Space and time form one combined four-dimensional framework called space-time. And everything moving through it follows the straightest possible path called a geodesic.
Now we're ready for gravity.
Great, let's go.
Remember how everything moving freely follows the straightest possible path through space-time?
Yes, a geodesic.
Exactly. A massive object like Earth curves the space-time around it, changing what that geodesic, or the straightest path, looks like. Imagine an object drifting freely through empty space. With nothing around it, it simply continues in a straight line.
Makes sense.
Now place Earth in its path. Earth curves the space-time around it, so the straightest possible path is no longer the one it was following before. That path now bends toward Earth. The object isn't being pulled off its path by a force. It's still following the straightest path available to it. It's just that the path itself has changed.
But how can a curved path be the straightest?
Good question. Imagine you're walking across Earth. From your point of view, you never turn. You simply keep walking straight ahead. But someone watching from space would see your path curve around Earth's surface.
So, to me, the path is straight, but to someone else, it's curved.
Exactly. You were following the straightest possible path on Earth's curved surface. To you, it felt perfectly straight. To someone watching from space, it looked curved.
That makes sense. But there's still something I don't understand.
Go on.
I understand why an object that's already moving near Earth follows a curved path. But what about an object that isn't moving? Suppose I'm holding an apple in my hand, and I simply let go. I don't throw it, I don't push it, I just release it. If gravity isn't a force, what makes it start moving?
That's an excellent question. The mistake is assuming the apple needs a force to start moving.
Doesn't it?
Not in this case. While you're holding that apple, your hand is constantly exerting an upward force on it. Without that force, the apple would already be following its natural path through space-time. It's geodesic.
So, my hand is actually stopping it?
Yes, your hand is preventing the apple from following the path it would naturally take.
So when I let go, it simply resumes following that natural path.
Exactly. And near Earth, that path leads toward the ground. Now, here's the interesting part. When the apple reaches the ground, the same thing happens again.
Same thing?
Yes. The Earth's surface now exerts an upward force on the apple, preventing it from continuing along its geodesic. If the ground suddenly weren't there, nothing would stop the apple. It would simply continue following that same path. In fact, that upward force from the ground is what you experience as weight.
So when the apple is falling, it's actually weightless?
Exactly. A freely falling object experiences no force. Locally, it's no different from an object drifting freely through empty space. Both are simply following their natural, straightest paths through space-time. They're geodesics.
I think I'm starting to get it. It's definitely not easy to picture, but I think I understand the idea.
That's perfectly normal. General relativity isn't intuitive.
Well, now that I finally have some idea of what gravity actually is, how does it slow down time?
It doesn't.
What?
At least, not in the way you're imagining. Mass curves space-time. Gravity is simply what we observe because of that curvature. One of those observations is that objects follow curved geodesics. Another is that clocks at different places tick at different rates. We call that gravitational time dilation. But it isn't gravity acting on time. It's another consequence of the same curved spacetime.
The same curvature of space-time that changes the paths objects follow is also what makes clocks tick more slowly near a massive object?
Exactly. Mass doesn't just change how objects move through space. It also changes how time passes. The closer you are to a massive object, the more slowly your clock ticks compared to one farther away.
Then, why do we still use the word gravity?
Because language doesn't change as quickly as science does. The word gravity had already been used for centuries before general relativity completely changed our understanding of it. Today, when physicists say gravity, they're often using it as a convenient shorthand for the observable effects of curved spacetime.
Gravity makes things fall, and gravity slows time are really just shortcuts?
Exactly. They're convenient ways of describing the effects of curved spacetime, even though they can give the impression that gravity is a separate force acting on objects or on time.
One last question. Why does curved spacetime make time pass differently?
That's the deepest question you've asked today. General relativity tells us that clocks tick at different rates in curved spacetime, and it predicts those differences with extraordinary accuracy. But if you're asking why spacetime has that property in the first place, today's physics doesn't yet have an answer.
So, even after all this, there's still no answer to why spacetime behaves this way?
Not yet. Every scientific theory has a boundary. General relativity tells us how space-time behaves with astonishing precision. But why space-time has those properties is a question that still lies beyond it. And perhaps that's exactly where the next great discovery begins.
I came here thinking I'd understand why gravity slows down time. Instead, I discovered I was asking the wrong question.
Best answers don't just change what you know. They change the questions you ask.
Professor and I aren't done yet. Next time, we'll leave the science behind and put Einstein himself in the hot seat. So subscribe. And until then, stay curious.